Okay, so last time we put a few examples here. Let's look at the first one. Again, another fairly common problem type that you'll see with these limits. They'll give you a piecewise function and then ask about the limits. So I asked about one of these. They could also, again, ask about from the right or from the left and things of that sort. Let's go with A. So our function is this guy. Let's do the first part. How do you find the limit as x approaches 1 of our function? Yeah.
It applies to the top one because x can't equal 1. So we're looking for how close it gets. So it would be the limit of
Well, I wouldn't say that. I don't want you to think of the limit of saying, oh, we can't be this. I want you to think it's not necessary.
It's not what we're
but it's
looking
not
for.
necessarily that. Any other ideas? Do you kind of realize what's going on? Yeah?
Plug into Piecewise or like equations and then.
Who said it would not be?
Right, this is where whether it's like greater, or equal to one, or just, wait, no, it's, yeah, greater than one or just greater than one. So plug in one first,
Okay, plug it in where?
get into the equation, see which one comes to one.
What do you mean which one comes up true? Explain.
So like you know which equation exactly to use, or you need to use both of them.
So that's the question. We're approaching 1. Notice that our function is broken up around 1. In terms of left and right, are they both the same? Like, can you describe one differently? How would you describe where this one applies?
Wouldn't that be on the left side?
Right, this applies to the left of 1. This applies to the right of 1. Right? And 1 is the guy I care about. However, our function is doing 2 things on either side. So this puts us in the situation where we have to worry about, well, do the left and right actually agree? Right? So at this point, because it's broken up around 1, which is the point we care about, you'll actually consider 2 limits here. You'll actually talk about coming from the left and talk about coming from the right. So from the left, if I look at x as approaching 1 from the left side, this means I'm a little less than 1, and I'm getting closer to 1. The part of this function that deals with the less than 1 is that guy. So I just need to find the limit as x approaches 1 of this, and that tells me what's going on the left. And you'll find that that is 3 here. Then I need to worry about, okay, what's going on to the right of 1. And that means your x is a little bit larger than 1. Okay, so this means your x is larger than 1 and you're coming down. Here your x was less than 1 and you're moving up. Okay. So that means now we need to look at the bottom function and see what is this doing when x gets close to 1. But that's an expression that you can just plug in 1. And if I plug in 1 for x, I would get 1. So these 2 together would tell us what? It does not exist. The limit as x approaches 1 of x does not exist. Okay? So 1 was the important value, and our function here tells us, oh, to the left and to the right are different things. That immediately makes us worry about the one-sided limits. So I jumped into finding the one-sided limits. So in this case, I needed to use both parts of the function, and I needed to make sure that they actually agreed, they actually matched up at the end. And it turns out that they didn't, and so the limit does not exist. Let's look at part 2 though. What if we're looking at the limit as x approaches 0 of x? What would you say is the answer here?
So I would use the first like function because it 0 is less than 1 and
Yeah, so if our
So
x is
I-
approaching 0, we're definitely nowhere close to being bigger than 1, right? We're super far away from 1. So this guy doesn't even apply. This would only apply to x values that are larger than 1 or equal to. 0 is squarely in this region over here. And so I would only look at one part of this function. I'm only looking at this when the limit approaches 0. So the limit as we approach 0, f of x is definitely going to be the limit as x approaches 0 of the 2x plus 1. Now you look at that, how would you find that limit? Well,
you plug in
step
0.
1, plug in. So that answer is actually 1. For a similar reason, if someone were to ask you in this scenario, what is the limit as you approach 3 of f of x? This one clearly doesn't. This one clearly does not apply because if you're less than 1, you're nowhere close to 3, right? You need to be super close to 3, and so this would mean you're only looking at the bottom function. And so now you worry about how would I find the limit of that? Well, it's something you can plug in. Now you would just plug in 4 minus 3 times 3 times 5. That would be the answer there. Now, if you want, and it's not necessary to do this here, but to kind of see what's going on, we could actually draw a picture here. So from 1 to the right of 1, we are 4 minus 3x. If I plug in 1, that would start at 1 here. So this starts at 1. And 4 minus 3x, that actually has negative slope. The graph would go down like that. So it's a straight line going down. To the left of 1, I have a line with positive slope passing through the y-intercept 1. It would look like that, where this guy's at 3. And my x needs to be negative a half for it to pass through. So that's actually the picture here. So now if you actually look at the picture, if somehow this notation confuses you, you always have the option of, well, I don't know how to plug in or do whatever here. What would the graph look like? And this graph is something you should be able to graph with quickly. Clearly you can see here, as we're approaching 1, the y values don't match up. So that's not going to exist. Versus, if we're looking at 0, we're over here, the y values are definitely matching up here from the right and the left. They're converging to 1. And if we're worried about 3, which is somewhere over here, they'll definitely match up, right? I just plug in the number. So with piecewise functions, one thing you have to be careful about is if the number you're approaching with the limit is actually one of the numbers where the function breaks into pieces, you have to consider the one-sided limits. You have to do both sides of that number. See, does the left and the right side agree here? And that can determine what the answer is. But as long as you're not at one of those numbers, you pretty much pick the function that is in the region you care about. So if you're 0, you're definitely over here, whereas if you're 3, you're definitely over here. You look at one part at a time, and you find the answer that way. So yeah, so this one did not exist, this one was 1, that one was minus 5. Let's look at example B. What do you think, sir?
Oh, okay.
Yeah.
And substitute
So the first thing you think, can I plug in? There's an x in the denominator, x is approaching 0, no, can't plug in. Next thing you think, can I simplify the plug in? And the answer would be yes, or at least we don't know, more than likely, because see that here is a complete square, which means I have the option of expanding stuff. Maybe I'll expand stuff and things will cancel and we don't know. So I would actually try step 2 here to to see if it works or not. What is this?
X squared plus 2x plus
Right.
1.
Don't forget about, you can't distribute powers across sums. All the algebra rules still apply.
Minus
So that would
1
be this minus 1
over x.
all over x. Now you notice, hey, this actually kills that.
And then you do x parentheses.
Now there's a common x, right? You factor that out.
X plus 2 and cancel x. So the limit would be 2 because you're
Right. So now you're at a state where you can literally just plug in. So the limit is 2. So that's algebra. So basically, you try to plug in, you realize you can't, then you see, can I simplify to plug in? In this case, you could, and it did simplify into something nice. I do want to mention something here. Notice that you keep writing the limit notation until we actually take the limit. Right, taking the limit means you've gotten to a point where you can actually plug in and determine exactly what the limit is. But until we do that, we kept bringing this symbol with us to show that we didn't take the limit yet. We're all simplifying here. We're just leaving the limit alone, simplifying, and then we got to here, okay, now we can actually apply the limit. Right, so I'm trying to figure out the limit. Limit of this is equal to the limit of that is equal to the limit of that, going all the way down. And so that one, the answer to that limit is 2. What about C? So we see this guy, limit as x approaches 0 of that. What do you do? Right. So you would say, can I plug in x equals 0? The answer is no, because you would divide by 0. So now you're like, can I simplify to plug in 0? And we've seen many examples like this. The trick to simplifying something like this here would be to rationalize the top by multiplying and dividing by the conjugate. So 4 plus x plus 2 over 4 plus x plus 2. Now of course that makes the numerator look like the difference of squares. So it'll be this squared minus that squared all over x times 4 plus x plus 2. So here, now the 4's would cancel, 4 minus 4. So I'm just left with x over x, 4 plus x plus 2. X's would cancel. Just write a line here because it's a common mistake to just think that it goes away. No, there's a 1 coming in its place. And at this point, can we plug in 0? Yeah, right, because if we plug in 0 at this point, the denominator is not 0. So I would just get
1 over 4.
1 over, right, the square root of 4 plus 2, which is 1 over 4. The limit here is actually a quarter. You see, I didn't need to know what the graph of that looks like to determine that. The step 2 helped me figure it out. Yeah, so something like that, the limit is a quarter, and that's how you do it. You'd actually simplify. And these examples are, of course, just me showing you that your algebra can come back to haunt you at any point, even when you're in a new topic like limits. You have to remember how to simplify various situations, which we looked at all these situations before. And this one is actually no different, because you can't plug in x equals 0, so now you want to try to simplify. How do you simplify this?
You multiply
By?
1 over x plus 2 by 2 and 1/2 by x plus 2.
But you're combining the fractions in the top. So the quicker way is to multiply and divide by the LCD. Kill 2 birds with 1 stone.
Yeah.
So it's like you're combining fractions in the top and at the same time doing the keep, change, flip maneuver in one step. So this multiply out that, and then this multiplies straight across here. So you multiply and divide by the LCD, that's the quickest way to simplify a complex fraction. Multiply this by the first one, the x plus 2's cancel, you're just left with a 2 minus, multiply this by that, the 2's cancel, you're left with an x plus 2. It is very important that you remember there should be parentheses here.
4.0.
What did you say?
I was talking to something.
X plus 2 over, now this is just x times 2 times x plus 2. Now in the top, the 2's are going to cancel, and you'd be left with minus x over x times 2 times x plus 2. At this point, you can cancel the x's, and now at that point, you can actually plug in x equals 0, because now you would look like this guy. And if you plug in x equals 0, you won't get 0. You actually get a number.
Negative 1 over.
You get a negative. So that limit is negative 1. Any questions on that one? So the first one's a little sketchy. The idea there is they tell you a piecewise function. You deal with it very differently if the point you want to take the limit at is one of the points where it's broken up. Because then you have to consider both sides of that, and you have to consider several functions. If one of the points you're taking the limit at is squarely in the domain of one of these two, you just worry about taking the limit of that part and not the others. In these situations, we couldn't plug in according to step 1, but we could simplify these, unlike the 1 over x squared example. So here are some, you can have various things looking various different ways.
It fell out.
Yeah, actually get something. I think we should have enough battery life left over though. You probably don't have to worry about it. Okay, yeah, we're
Oh, that's just for that.
and then you would have, right, so you can have various situations. You might have to expand parentheses, conjugate, you might have to multiply and divide by LCD. All these guys will just apply. So all our previous algebra things that we were looking at, they still apply, they will always apply. Now we're going to talk about a special technique. Special situation here. Yeah, we have enough time. Special situation here. Limits at infinity of rational functions. Special technique / situation. Limits at infinity of rational functions. These guys also show up often, and it turns out if you see one of these guys, it's actually a very good thing. These are some of the easiest limits to figure out, other than the ones where you literally have to plug in the number. These are pretty much as the easiest it's going to get for you. But the thing is, they tend to look scary, but the trick is they're not nearly as scary as you think. So recall a rational function. This just means it looks like p divided by q. where P and Q are polynomials. Q is not 0. Now the principle I'm going to tell you here can be generalized to other kinds of functions, but we only need to know them for polynomials. So if we're dividing polynomials and we want to figure out something like this, taking the limit as x goes to either positive infinity or negative infinity, the rules are going to work out the same, of something that looks like that. So I'm going to tell you the rules, we're going to apply the rules. I might tell you why the rules work out the way they do, but I'll tell you that afterwards. So it turns out, if you see something that looks like this, it's really only one of 3 possible cases. So all you need to do is know where to look to figure out which case you're in, and then you can actually get to the answer pretty easy. Turns out that if you have a limit as x approaches either positive or negative infinity of something that looks like this, rational functions, there are 3 possibilities for what the answer will look like. There are no more. There will never be any more. One of 3 things are happening. And I can kind of even tell you what the answer is going to be like. One possibility is that the answer is 0. Specifically the number 0. It's going to be the number 0. And how do you know the answer would be 0? Is you would look at the degrees of the polynomial. Now remember, the degrees just means the highest power that appears in a polynomial, right? So you look at the degrees of the polynomial. If the degree of Q is larger than the degree of P, you will always get 0. It does not matter how the polynomials look, what are the specific polynomials involved, doesn't matter. Identify the highest powers. If the highest power is in the bottom, the answer is going to be 0. Right? This we might refer to as top heavy, bottom heavy. So the highest power is in the bottom. We might refer to this as bottom heavy. Right? The larger power is on the bottom. And bottom heavy is just the phrase I want you to write down. I'll actually show you how you can actually think about this computationally, but it's really not necessary. So if I give you a limit that has this form and you realize that the highest power is on the bottom, you are just going to tell me, oh, this is 0 because it's bottom heavy. You write down that phrase and that's you showing your work. I'll just assume you know what you're talking about when you write that. Just make sure you're in the right situation to write it. Right? So remember what the degree means. It's the highest power. So you look at the highest powers. If the highest power is in the bottom, the answer is going to be 0. Here's the other situation. It will be the leading coefficient of P divided by the leading coefficient of Q in the event that the degrees are actually the same. So if the degree of P is the same as the degree of Q, that's actually going to be the answer. Now the leading coefficient is just the coefficient of the term with the highest power. So leading doesn't mean it comes in front. Don't look at it that way. Leading means find the guy with the highest power. That coefficient is called the leading coefficient. Coefficient of the term with highest power. So you look at this expression, identify the highest powers. If the highest powers are the same in the top and the bottom, you would take the number that's in front of the highest power in P divided by the number of the powers of the highest power in Q. And this is usually referred to as the ratio of leading coefficients. So if you write down that answer and you write down this phrase, ratio of leading coefficients, I will take that as you showing your work. I'll assume you know what you're talking about, and I'll give you full credit for that answer. So that's the second situation. The last situation is one that you have to be a little bit careful about. So it turns out the answer will be infinite. However, it can be plus or minus infinity. You just have to pay attention to the signs. To know which is which. Pay attention to the signs and powers involved. So you just want to make sure that, well, if you're going to have like a negative number divided by a positive, overall it should be negative, things of that sort. And this happens if the degree of P is the bigger one. In other words, the largest power is in the top. We would call this top heavy. So if I ask you a limit of this form, you say, oh, it's positive infinity because it's top heavy. That's showing your work and assuming that you identified things correctly and you paid attention to the signs, that's good enough. Let's look at some examples where we're going to apply this. A limit as x approaches infinity. 4 plus x minus x cubed over limit as approaches infinity of 17x cubed plus x. Let's actually find these guys. Okay, what do you think is the first one?
Bond movie.
Hmm?
Bond movie.
Right, well, what's the answer? Right, so you'd look at that, and the thought process would be, okay, look in the top, highest power, x cubed. Look in the bottom, highest power, 2x to the fifth. The highest power is on the bottom, it's bottom heavy, 0. And then you write bottom heavy. And that's it. Yeah, that's it. Moving on. What is this one?
It's top.
Ratio of leading coefficients, we get what? 17 over -2. The sign is important. So you look at the top, highest power, x cubed. Look in the bottom, highest power, x cubed. Highest power is the same in the top and the bottom. The leading coefficient, therefore, is 17 in the top. The leading coefficient in the bottom is -2. It takes the sign. So the answer is going to be 17 divided by -2. and then you write ratio of leading coefficients. So here you can see, this kind of looks scary. It looks like one of the scariest problems we've seen here, but it's actually the easiest problem we've done today. Because you can essentially ignore everything except the highest powers. That's basically the idea that this is trying to get through your heads. Highest powers on the bottom, it goes to 0. Highest powers on the top, it goes to plus or minus infinity. Highest power is equal, goes to the ratio of leading coefficients. What about this one here?
Top heavy.
Okay, so what is the answer?
Infinity.
So here, those are both the highest power in the bottom is, in the top is x to the 5th, highest power in the bottom is x squared. It's definitely top heavy, so I know it's going to be infinite, but which one? Positive or negative?
Positive.
And then you can write, we'll talk about this a little bit
Top.
later. This is top heavy. What about this one?
It's also top.
It's again top heavy, yeah. Highest power is this, highest power is that. So you know infinity is going to be an answer, but is it positive or negative?
Positive.
Why is it negative?
Oh,
There's a
yeah.
sign right here, negative infinity. Pay attention to the signs. This isn't going to infinity, it's going to negative infinity, which means your x values are going negative, which means x to the 5th is also negative, which means 2 times x to the 5th is negative. So this is a negative charge on the top. In the denominator though, our x is squared, which means even if I'm plugging in a negative number, that's going to give me a positive number. Then I multiply that by a positive 5, so at the bottom will have a positive charge. Here I have a negative charge over a positive charge, and I know it's infinity. It's negative infinity. Okay, so that's what I meant by paying attention to the signs. Here that was a non-issue. Our x was going to positive infinity, which means all our x values are positive numbers. Raise it to the 5th, it's a positive number, multiply by 2, still positive. Same thing here, x squared, positive number, multiply by positive 5, positive number. I have a positive divided by a positive. And that's why this was positive infinity. What about this one?
It's top.
It's top heavy. Highest power in the top is x to the 4th, highest power in the bottom is x squared, it's top heavy. So we know infinity, it's an infinite answer, but we need to know which infinity, positive or negative.
Positive.
Why would you say that? It's one or the other. They all said positive, that's wrong. You know what? Yeah. Sure.
Because,
But why?
the negative 6, so even if you have,
Yeah,
an
there's a
even
negative
exponent
6.
on the, you will, so you have an even exponent, the 4th,
Yeah.
it's the 4th, so you would, that would give you a positive 1, but since you have a negative 6, it would give you a negative, and negative over a positive is negative.
Yeah, so this was a negative charge, and this is a positive charge. Okay, what about this one?
It's top heavy.
No,
Positive.
it's negative.
Negative.
Still negative. I didn't want this example to give you the impression that, oh, if he changes the infinity, you just change the sign. No, that's not what's going on. You still have to pay attention to the particulars of the problem. Here, I plug in a negative number into x, but then I raise it to the 4th power, it becomes positive. Then I multiply by negative 6, so this still has a negative charge. If I plug in a negative number into x, I square it becomes positive, it stays positive, it becomes positive, and then I multiply by a positive 2, it's positive. I'm still in the situation where there's a positive and a negative charge. So it's negative infinity. So here is right. All of these is top heavy, but you have to pay attention here. So you know the answer is infinite in these cases, but you have to be aware of which infinity it's going to be. And that just requires you to pay very careful attention to the signs and to the powers. You have to remember that, well, if you plug in a negative number, raise it to an odd power, it stays negative. And if you multiply by a positive number, it stays negative. All those little things you have to pay attention to. But as far as limit problems go, even these still aren't that bad. You just need to pay a little bit careful attention to the signs and you'll be fine. So the highest power is at the bottom, it's always going to be 0. Highest power is at the top, as it was in these last 4, it's going to be either plus or minus infinity. Pay attention to the signs. Highest power in the top and the bottom are the same. You just take the number in front of the coefficients, and put them in a fraction. And for these, as far as showing your work is concerned, you can simply just write down these phrases. Now, you don't have to know this, and you also don't have to know why, but just in case some people are curious, let me illustrate why the answer would look like that on the first 3. So why? It's because we have a technique to deal with these. And that is divide top and bottom by highest power of x in, and it turns out you always do it for the denominator. Always in the denominator. So if you had something like realize the highest power in the denominator is x to the 5th. And so what you'd actually do is you go in, you divide everyone by x to the 5th. Since you're dividing both the top and the bottom, you're not changing the value anywhere. It's like you're multiplying by x to the 5th over itself. Then what you'd realize is going to happen is that you can now simplify. So this would be 4 over x to the 5th. Plus 1 over x to the 4th, minus 1 over x squared, over 2 minus 3 over x cubed, plus pi over x to the 4th, plus radical 2 over x to the 5th. And so now, the thing is, these guys that we are now looking at, we kind of know how they behave very well. If the top is a constant and the bottom is going off to infinity, we know that goes to 0. Because you have a fraction where the numerator is very small, the denominator is very large, overall the fraction is going to be very small. So this is going to go to 0, 0, 0, 0, 0, 0, and you end up with 0 over 2, which is 0. And it turns out that if your highest power is in the denominator, something like that is always going to happen. You're always going to have a bunch of fractions in the numerator where they're all going to 0. If you do that when the highest power is the same, if you look at this one, where the highest powers were the same, you do that maneuver, you would have 17x cubed over x cubed, plus 3x squared over x cubed, plus 1 over x cubed, over 5 over x cubed, minus x over x cubed, minus 2x cubed over x cubed. Right? That was the highest power in the denominator, you divide by that. You could simplify this to, well, that's just 17 plus 3 over x, plus 1 over x cubed, over 5 over x cubed, minus 1 over x squared, minus 2. Realize all of these guys would go to 0. And so you'll end up with 17 over minus 2, which is what we know is the answer.
Then why don't they go to 0?
Because we have a fraction where the top is a constant and the denominator is going to infinity. For each of these, for example, you would know what the graph would look like. Right? So if you have 1 over x to the n, and n is odd, it's going to look like that. Now if you're going off to infinity, this is going to 0. Similarly, if you have 1 over x to the n, and n is even, it looks like this. And again, as you're going off to infinity, your y value is going down to 0. If you have a fraction where the denominator is getting large and the top is very small, it goes to 0. Right? A fraction gets smaller the larger, the more pieces you divide it into. Right? 1 over 10 is larger than 1 over 1,000. It's larger than 1 over 1,000,000, which is larger than 1 over 1,000,000,000. The larger the denominator, the smaller the fraction. By a similar mechanism here, if we were to divide everyone by x squared, I'd have all these guys are fractions. This guy here would be 5, but that guy would have an x cubed. And he's going to go off to infinity while everyone else is going off to 0 or staying constant. So the entire fraction as a whole is going to go off to infinity. Right? So that's kind of the background, that's what's happening in the background, but you don't need to know that and you don't need to even show it. Just know the 3 situations you can follow yourself in, either bottom heavy or top heavy or ratio of leading coefficients. So that's one of the special techniques there. That's kind of all we need to know about limits. Of course, the situations can vary, but what I told you, you can deal with any limit problem. So, first thing you need to do is you need to remember the strategy. So step 1, try to plug in, can't work, simplify to plug in. 3, if you see something really crazy, then it's probably this guy. Just make sure the limit is going to infinity. And then and you have the ratio of polynomials. Otherwise, you check the graph or plug in numbers, but ultimately you can get to an answer in one of these ways. Now, here's another concept we're going to talk about. It's in the same section, but it's a slightly different concept, and that's the idea of continuity. So it involves the use of limits, but it's a separate idea. So this will go back to the bonus in the quiz. I want to ask you about, was the function continuous at this point? Did it possess the property of continuity? Okay, so now I'm going to talk about what that is. I'm going to start out with the mathematical definition. Ultimately, when you want to say something is continuous, you have to go through this definition. But then I'll talk about intuitively what it actually means. Definition. We say a function, f of x, is continuous at x equals a if the following is true. If the limit as x approaches a of the function is the value of the function at a. If this equation is true, we say the function is continuous at a. If it's not true, we say the function is not continuous, or the function is discontinuous at a. So in the quiz, when I ask you, is the function continuous at x equals 2, all you needed to do is check, what is the limit as x approaches 2? It would give you a value. And then you ask, what is f of 2? Is the function actually filled in at 2 somewhere? And you find the value. And then you check that they're equal. If it's equal, the answer was yes. If they're not equal, the answer is no. We can also talk about a variation on this, a stronger, more generalized version of saying continuous, we can say f of x is continuous. Period. Right? So this says continuous at a specific point, but there's an idea of being continuous in general. Right? So we say f of x is continuous, right? Not specifying a point, if it is continuous at all points in its domain. In other words, if the point is in its domain, this equation will be true for every such point. So if the continuity equation works everywhere in the domain of the function is called a continuous function. There are 6 kinds of elementary continuous functions. Elementary means we study them in undergrad calc classes because they're nicer to deal with. You can have non-elementary functions that are really kind of sticky. A polynomial is such a function. At every point in the domain of the polynomial, which is the entire real line, it will have this equation being true. Rational functions, this is true for rational functions. Meaning, as long as we're in the domain, as long as the denominator is not 0, this equation will work for every single point of a rational function. Radicals. As long as the square root is working, meaning it's not even and you're plugging in a negative number or anything like that, any permissible point, this equation will be true for a radical function. So we look at y equals the square root of x or y equals the cube root of x. Those guys are continuous. At every single point where that works, this equation will be true. The last 3, they are elementary, but they're not really in our syllabus. Exponential functions. So example, y equals e to the x, or y equals 2 to the x, or something similar. You can have log functions. Example, y equals ln x, or y equals log to the base 2 of x, etc. And trig functions. All the trig functions, sine, cosine, tangent, cotangent, cosecant, cosecant, and secant, these are all actually continuous functions. Now the last 3 you don't have to worry about, it's not in our syllabus. But you should know, every time you're looking at one of these 3 functions, which we have spoken about, you are looking at a continuous function. These functions have the property that as long as you're in their domain, this equation will be true. It's very rare to be a continuous function, so not many functions are continuous. The continuous ones, we obviously like them a lot, but it's actually very strange to be a continuous function. Even very simple examples. I can look at this example. If you look at that function, not a complicated function, a very simple piecewise function, you might notice the domain is all real numbers. It is actually defined for every single x value. No matter what you tell me as an x value, I can tell you the y value. There is an output. It is defined, but it is not continuous at x equals 0, for example. That 0 is the only point where it kind of breaks down. How would you know? Well, this function says it's 1 if you're bigger than 0, so its graph will look like that. It's -1 if they're less than 0, so its graph will look like that. So now someone asks the question, what is the limit as you approach 0? Does not exist. So I found a point that the function can give me an output. In this case, f of 0 is the number 1. This side of the equation behaves. That side did not exist. Okay? So because the limit is not equal to the value of the function, I say it's not continuous. Okay? So this is not a continuous function, even though its domain is actually everything. So being continuous is a very rare thing. You can work for every number, but being continuous is a step above that. This kind of illustrates what we mean intuitively when we talk about continuity. Notice that there's a gap here. And when we're talking about continuity, that's the kind of thing we want to describe. Or we want to describe the lack thereof. Okay? So continuity means the function just continues. You can just keep drawing it, no problems. You don't even have to lift your pencil off the page. It's just continuing the graph is just continuing. Okay? Continuity breaks if there's a gap, there's a hole, there's a jump, there's some kind of disturbance in the function where you kind of have to jump over something. Okay? Now when that happens, we say the function is not continuous. Okay? And to describe that in words, you can talk about that intuitively, but when it comes down to formulas, you need a very mathematical way to say that. So how do you actually say to someone, there's a break in this picture? It turns out, the math way to say that is this equation does not hold. Right? This equation condenses that very intuitive idea of there being no gaps. Well, let's actually look at how we know that would be the case. So we're saying as long as that equation holds, there's not going to be a gap or a break or a jump or anything bad. The moment we have one of these things, the reason is that equation failed. So let's look at some illustrative examples here. So let's look at some ways that things can break continuity, not continuous. So let's look at some examples here and let's look at what actually happened. Here's a very nice way to not be continuous, right? It's almost continuous, there's just a very small point. Function like that, right? It has a hole in one single point. Now that means it's not continuing. Like I'm drawing this, I have to jump over that point to continue. Right? There's a break, there's a gap. There's something there disturbing the function where the function can't exist there. Right? So that's a gap. Another way a function cannot be continuous is say something like this happens. Right? Obviously I can't just draw this without lifting my pencil off the page. I have to jump and continue the picture. Or it can happen vice versa. You know, kind of like this one over there. Right? Again, I had to make a jump. It's possible for something like this to happen as well. There's a huge infinite chasm between one side and the other. Again, I can't draw this without lifting my pencil off the page. I have to draw this side, jump over, and then draw that side. Right? So this idea, the idea that I have to break the graph, I have to break the line, break the curve, it goes off into pieces, or there's a hole, or there's some sort of disturbance. That's the idea of not being continuous. Versus, so let's say not continuous at x equals a. Let's actually specify a point here. And let me call this point here a. Alright, so this is what it means to not be continuous at the point A. Versus, we can be continuous at the point A. And that's just a graph like what you might think. Like when you pass through the point A, you can just pass through and not worry about it. You can just continue to draw the function with no disturbance. Right? So that is an example of being continuous at A. So now, how do you go about describing the idea? When a break happens from when it doesn't happen? Well, it turns out you can describe the idea very concisely just by taking limits into the mix. So for example, if you notice here what's going on, let me give these guys some made up values. Values don't even matter really, it's just the idea. Say that's at B, that's at C. So what's happening over here? Well, you would notice that if we look at the limit, what is the limit as x approaches a of f of x?
There's a break, so it's not, there's a jump.
Okay, so what is the limit? The
Okay.
limit is b. Okay?
Oh,
Limits don't care about not being there. Remember that concept. Limit here works, limit exists. Okay? The limit here would be b. As I get close to a from either side, the y coordinates of this graph, they both converge to b. The limit exists. The fact that there's a hole there, limit doesn't care. Okay? There's a big difference between continuity and limits. Okay? However, what if I look at f of a? What is that? Yeah,
Does it exist?
that's undefined. So the limit works, it's the function itself that didn't. And so here, obviously, the limit is not equal to the function at that, the value of the function at the point. So whenever the limit exists but the function doesn't, what that causes is a hole, right? So even if I didn't know what the picture of the f looked like, but someone told me this information, oh, the limit is this, but the function isn't there. I would know whatever the picture looks like, at that point there's a hole. Yeah.
When do you use the term does not exist in undefined?
Undefined for functions, does not exist for limits. Now if you look at this one, what is the limit here?
oh, B, no.
Does not exist. Why?
Because there's
There's no one unique value.
And
Okay,
from the
explain,
left
no
side-
unique value, explain that idea.
Like, the left side
Mhm.
approaches B, the right side approaches C.
Exactly. Limit does not exist because there's no unique y-valued approaches. It means you're looking at the left and the right side and they didn't match up. So the limit here did not exist. Does the function itself exist?
Yeah.
What is it?
is
B.
B.
So in this case, the limit didn't work, but the function did. Now whenever that happens, it means there's a jump. Not only is there a single hole missing, but there's literally one side of the function that's moved away from the other side of the function. This one is going to be similar. The limit does not exist, but f of a is c in this case, but you still have the same problem. Those two aren't equal. It's possible for both of these to happen. So an example like this would be just as bad. Right? So C plus B plus A. In this case, both of them didn't work. So the limit does not exist and the function is undefined. Here, the limit does exist. It's actually infinity, but that's a problem because you can't actually define a function to be infinity. Once either of them is infinite, that's automatically a problem. F of a here does not is undefined. But even if it was a number, it's definitely not going to be infinity, right? You never have infinity as the output of a function. And you can look at any situation where there's a hole or a break or a gap or a jump. What happened was these two didn't agree. However, when everyone agrees, everyone is getting along. We get to something like this, and we see that the limit as x approaches a of our function is b. And we see that f of a is also b. These two are the same. The function and the limit both agree. This tells you continuity. That means the y values are converging as I get close to the point, and that point is actually filled in. I can just walk right across that bridge. No problems, no breaks. So that's the idea of continuity. I can just keep drawing the function, not lifting up my pencil. And it turns out you can actually know exactly when that's going to happen by checking these equations. Whether you know what the picture looks like or not, you can know exactly how it's behaving. And that's the power of knowing about limits. And this is why these two concepts had to be separated, right? This is why we didn't want the limit to worry about whether something is filled in or not. Because there are times when the situation you wouldn't be able to reconcile what's going on, right? So we want to talk about points being filled in as being defined by the function itself, and a limit as defining something else. The idea of getting close to that point. Right? So it's looking at the same function in two different perspectives, but whenever the perspectives come together, that creates a very special kind of function. That creates a function with continuity. So that's what it means for a function to be continuous. The intuitive definition, you can draw it without lifting your pencil off the page. There's no gap, break, jump, disturbance, nothing. Everything is hunky-dory, everything is fine, everyone's getting along, everyone agrees. That does not happen means the limit as you approach some point is not equal to the value of the function as you approach that point. And that causes a break, a gap, or a hole, or a jump, or something. So let's make that a little bit more specific. Let me break down the definition here. For f of x to be continuous at x equals a, right? So sometimes they'll ask you the question, is f continuous at this point? Like I asked you in the quiz, right? That will come up on a final or on the test or something like that. Sometimes they'll give you a picture, sometimes they won't. Sometimes they'll give you a formula. Either way, you should know what you're looking for. For f to be continuous, you have to, your thought process should be on you should focus on three things. There are three things that have to come together for f to be continuous at a point. One, f of a must be defined. You must actually be able to plug in the value in f, and it must give you a meaningful answer. Okay? Or on the graph, on that picture, whatever the a is, the corresponding coordinate must be filled in. Right? So that's the graphical way to determine. Right? So either as a formula, you can plug in the number and everything makes sense. You're not dividing by 0 or taking the radical of a negative or something like that. Everything makes sense when you plug in. That's the first thing that needs to happen. The second thing that needs to happen is the limit must exist. And you should be aware that, of course, sometimes this means you have to check sometimes. Need to check both the limit as x approaches a from the right of your function, and you need to check the limit as x approaches a from the left of your function. I mean, sometimes you have to look at those individually, make sure those match up. If they match up, then this guy's going to work. So you have to check the value of the function, you have to check the limit, and the third thing is the above must be the same. Whatever answer you get for 1 must be the same as the answer you get for 2. Right? So these 3 things have to come together. The function has to work, the limit has to exist, and they have to agree. Right? So whenever someone asks you, is the function continuous at this point? Those are the 3 things they're going to check. Does the function exist? Does the limit exist? Do they agree? Right? You go through these 3 steps, checking one at a time. And based on whether it's a graph or a formula, you now know how to check these, right? You know how to plug it into formulas. You now know, after today's class, how to find the limit. And now you're just going to compare them. So those 3 things must come together. Let's do some examples.
So on the quiz, it was continuous, right?
I think it was a different thing for each version.
I got B. And it
I
was
don't
a
remember.
closed.
One was and one wasn't. I don't remember which was which. The one that had the open circle was no.
Okay, so.
Because the one with the open circle failed here.
Yeah.
F did not exist. If you got the version with the point was filled in, the answer was yes, because it turns out all of these would have worked. So yeah, the versions had different
And
ideas.
on the graph, I was unsure because there was this question about zero, like find the limit of zeros. Would that be does not exist?
I don't remember. It depends on the version. Like the things were slightly different, so. And I don't remember who I put on A versus B. But let's actually just this. I'll post the answers later. You'll see. Determine where, and this is a lot of times how a question might be phrased. When they say where, it means they want you to tell you like the interval in which the x values will make it continuous. So tell us the intervals where these will be continuous. A. E will actually skip. I think I want to do like a major example to tie a lot of things together after we do derivatives. So I was going to draw a huge function on the board and we are going to examine the graph, but we'll actually put that off for a little bit. The lessons to be learned there would be the same lessons that we learned from the quiz. A. What would your answer be? Where is it continuous? It's continuous everywhere. That's actually a phrase, continuous everywhere. It means continuous on the entire line. And why? Y equals x squared is a polynomial. That was one of the examples. No. That was one of the examples where I said it was a continuous function. Continuous means it's continuous at every point in its domain. The domain of a polynomial is all real numbers. So any polynomial will be continuous for all real numbers, or we can say continuous everywhere. So A was actually kind of a throwaway. Let's look at B. Huh?
Everywhere except 2.
Everywhere except 2. Now,
Everywhere except -2.
so let's actually go through the check. Is f of 2 defined? So it's, the answer is no. So that automatically means not continuous at 2. But I can sort of write down what you think here.
So there's not continuous.
This has a denominator. At this point, you should worry about where the denominator is 0.
It's the same number. It matches. How is this if x does not equal to 2?
X equals 2 makes it 0.
It's -2. And this all becomes -2. So it's not.
Now you'd be able to say f of 2 is undefined. So not continuous at 2. The limit, by the way, does exist at 2. But we already know it's not continuous. You can note, what is the limit as we approach 2 of this function? How would you find that limit?
You would factor.
Right, this is one of those cases where obviously we can't plug in 2, so we try to simplify.
And
So
it
you
will, the
factor.
limit will be 4.
Right, we'll get 4. So the limit exists, but it doesn't matter. The function itself doesn't exist, so it's not continuous. Pretty much what happens is, everywhere other than at 2, it actually behaves like the function x plus 2. We've seen this behavior already. So there's like a hole at 2. So that's kind of the picture here. And you realize that other than at 2, everything is fine. Because if we're not at 2, this is just a fraction. It's going to give us a number, and it's going to work everywhere. So the answer here is that it's continuous everywhere except 2. So the answer here would be, as long as you're not 2 specifically, you're continuous. 2 is the only bad thing here. It's the only guy you can't plug in that the limit would work, but the function itself wouldn't. So that was B. What do you think about C?
It's not continuous.
Now that's a piecewise function, so we have a history with piecewise functions. Let's actually be very careful. So again, you'd notice that if not at x equals 2, we're fine. Right? So if we're not at 2, this is our thing, and it's going to be just some fraction. Everything will be fine. We'll be able to find limits by just plugging in the numbers, and everything will be actually fine. So what we're going to do now is check x equals 2. All right, so if we're not at 2, we're okay. But what about at 2? 1. Is f of 2 defined?
No.
No.
Yes, what is it? F of 2 is 0, so it's defined. Check. Second thing we're going to look for. What about the limit as x approaches 2 of f of x? Does that exist?
Yes.
Yes? What is it?
It's 4.
It's 4. It's actually the same guy we found over there. So looking at the limit, we'll realize that at the specific point x equals 2, it is 0. Limits do not care about being at the specific point, so I'd ignore that. For everywhere, including when we're approaching 2, that's the function. So I'm taking the limit as x approaches 2 of that function. We already did the work for it over there. It is actually 4. So this is also defined. phrase we use here is exist. So check. So step 1 and step 2 worked out fine. 3, what happens here? Now it breaks. Right? The limit as x approaches 2 of f is not the same as f of 2. Because of course 4 is not the same as 0. So we almost got through it, but failed on the last step. So it turns out that this one is also not working at 2. Other than at 2 it's fine. So the answer is again everywhere except 2. What you might realize happened here, if you wanted to look at a graph of what's going on. The graph again looks like this. When we're at 2. But what they did was, at 2, they came and they filled in the point 0. So they filled in a point 0. Okay, it doesn't matter. I still have, in order to draw this, I still have to jump over, fill in the point, jump back. There's still a break in the function. There's a gap.
So it would be not continuous?
Not continuous at 2 specifically.
Yeah.
It's continuous as long as we're not at 2. This was asked in the affirmative, right? It didn't ask you where it's not continuous. It asked you where it is. So if they ask you where it's not continuous, your answer would be at x equals 2. Asking you where it is continuous is pretty much everywhere else. Let's look at the last example. So here, our function x squared minus 4 over x minus 2, if x is not at 2, here it's 4, if x is 2. And we can go through that check, and just go through one by one, check the pieces. So again, realize not at x equals 2, we're fine. Right, so 2 is the only guy I have to worry about here. And so what I can do now is to check at x equals 2. Then I'm going to do 1. Is the function defined at 2? The answer is yes. When x equals 2, it gives me the value 4. 2. Does the limit exist at 2? The answer is yes. Not at 2, I'd be looking here. I would say the limit as x approaches 2 of that. Did the work over there? That's 4. 3.
Oh, yeah.
Does the limit as x approaches 2 of our function equals f of 2? The answer is yes. This means f is continuous at 2. This particular function is continuous at 2. And so the answer here would actually be, this one is continuous everywhere. So we got a lot of mileage out of this example. These two didn't work at 2, but this one did. And I want to appreciate why that was the case. And probably draw the picture for you here of what happens. So in this situation, what happened was, yes, we had that graph doing its thing. There was a hole here. This was 2. The hole, if it had been filled in, its location would be at y value 4. And someone just went and they filled it in. Right? That's what's happened. Right? So here we were this function, but we can't obviously be 2. So what someone did was they went to 2, they filled in 4, and so what you get is this kind of situation. So now you have something that there was a gap, but someone filled it in. So now you're in the situation where you can just keep drawing it and not have to break anything. Right? Here, there was a gap, no one even tried to fix it, that's definitely discontinuous. Here, there was a gap, someone tried to fix it, but they filled in the wrong point. They did a very poor job. It still has a break in it. But here, someone filled it in correctly. And this leads to another concept of removable versus non-removable discontinuities. So that's just a definition you should know. They might ask you that in a final. Is the discontinuity here removable? You would need to know how to answer that. We say a discontinuity is removable if we can do something like this. We can fix it without really changing what the function is doing. Right? We can maintain the spirit of the function, but fix the bad points. We say f of x as a removable discontinuity at x equals a if we can redefine it at a so that it becomes continuous. This is the idea of a removable discontinuity. These are what we call holes on a graph, right? On a picture that has a removable discontinuity, you will literally see a hole in the graph. That's how you know a discontinuity is removable. It's basically it's a discontinuity that's just a single hole. There's a single point that's out of place, and you just need to fill in that point. This is called a removable discontinuity. So those are called holes. So for example, y equals x squared over 4 over x minus 2 has a removable discontinuity. At x equals 2, right? So at x equals 2, the function does not work, it's not continuous, but you could literally just redefine it at that one point, and everything works now. Right? You could just redefine, let y do whatever it wants, whatever it used to be doing, but restrict it from doing that at 2, and just fill in 2 to be the proper thing. So I redefine the function at that specific point, and now all problems are fixed. So that's called a removable discontinuity. We can fix the discontinuity. There are some discontinuities that are not fixable. If f of x is discontinuous at x equals a, and it is and you cannot fix it by redefining f at a or a finite number of points. Then f is said to have a non-removable discontinuity. Sometimes they might use the word essential. These are the real big ones. These are the gaps or jumps. So a graph that looks like this, right, where it literally has to jump over what we call an asymptote, which we'll talk about next time, or this, right? Those are what we call jump discontinuities, and as you can see, it isn't just like there's a single point out of place. There's an infinite number of points out of place. To actually fix the discontinuity here, I would have to radically redefine the function. I literally have to take the top part and push all those points down, or take this and move all those points up. I'd literally have to shift an infinite number of points to fix this thing, right? And by that point, I totally undo whatever the function was doing. It'll just, I might as well think of it as a different function altogether at that point, right? There's no way to maintain the main goal of the function originally and fix that discontinuity at the same time. It's totally gone. Whereas with this one, it was totally fine except for that one point. I mean, filling that in, everywhere else it's behaving just the same, right? You're not changing the spirit of the function. But this one, if you have jumps or gaps, these are called non-removable or essential because you literally have to redefine an infinite number of points to fix it, and that's too much. That you totally destroy the function by doing that. So that's removable versus non-removable. There's one last thing I want to show you guys on the and that's just doing it in your calculator. So pull out your calculator and I'll show you how to plug this in. So if you're in the calculator section, you can actually find the limits. So you can write this. Well, you don't have to write this down, it's in a handout, but basically what you want to do is you want to go to the calc menu, which is on top. I think that's the F3. You want to find the limit command, and the syntax is the following. Once you enter the limit command, it'll open in parentheses. You're literally going to type out the function. You're going to put a comma. You're going to put x, because you're telling it x is approaching something. You're going to put a. And there's a fourth coordinate that's optional. So, optional coordinate. So this is if you want to find the limit as x approaches a of f of x, right? So the a, you put that like, type out the function, comma, x, comma, a. This part is optional. It's if you want to find the left or the right hand limits. You'd actually put 1 if you want to put from the right, positive 1. You would put minus 1 if you want to do from the left. Right, so you put a positive sign or a positive 1 if you want to go from the right. You put a negative sign or a negative 1 if you want to move from the left. And that's basically the syntax. That will calculate the limit. So let's just plug in some of these limits. And you'd be able to see. We'll just do a couple examples that we've done before by hand, so you can obviously know we did the right thing. The calculator agrees with us. Let me pick this up. would actually show up if I turned off all the lights. So can you see it? Yeah, it's kind of hard to see. Let me turn off everything. Okay, let's look at our last limit. So let's turn it on. Let's find the limit as x approaches 2 of x squared minus 4 over x minus 2. So if you're in the calculator section, you should know how to find limits on a calculator because it might come up. So as I said, you want to go to the calc menu, which is here. That's F3. So you're going to press F3. There's a bunch of calculator. You'll notice calculator functions. You can find derivatives, integrals, limits, sums, products, a lot of cool stuff. We actually want the third option, which says limit. So we're going to scroll down to limit.
Not this one.
Okay. So now you see limit with open parentheses come here, and then we're going to follow that syntax. We're going to type out the function, comma, x, because you're telling me I want the limit as x is approaching this. And again, that's because this calculator can use multiple variables, so you want to specify which variable you're taking the limit with. So let's type out the first one. So we would need parentheses here. We know that because we build in good habits. A lot of times when students don't get the right answer here, it's because they don't use parentheses correctly. They don't think in terms of parentheses. So I need x squared minus 4 divided by x minus 2. If you don't put the parentheses, it's going to think you're looking at x squared minus 4 over x and minus 2 separately. Your calculator will think of these as 3 separate things instead of one fraction if you don't use those parentheses. The parentheses are important. So that would be the first part, comma, x, comma, now I want to approach 2, so I'm going to put in 2. Now at this point, I can close the parentheses. That fourth space is optional, as I said. So you can close the parentheses here if you want to find the limit as you approach 2. And so now, if you press E, enter, there, it tells you the answer is 4. And you can know you computed the same thing. It'll copy down the limit that it told you over here. So you can also notice, had I typed this incorrectly, you should realize. So let's say I was very bad and I decided not to put the parentheses. And I just went x squared minus 4 divided by x minus 2, comma, x, comma, 2. You see here, it clearly thought of that as something else. Okay? Without the parentheses, your calculator will completely misunderstand you. You need to learn how to use parentheses properly. Right? Very rookie mistake. That happens all the time. Surprisingly, what happens a lot of the time is students don't remember how to do this in the first place. But even the people who remember how to do it, another issue is that they can type things in wrong. So be careful with your parentheses. That's one thing you need to be aware of. Let's see how you would actually do something from the right, or on the left. First, let's look at this example here. Again, let's go calc, limit. Let's look at 1 over x. 1 divided by x, comma, as x approaches 0, close. Now we saw that that does not exist. It's going to tell you here, undefined. That's it. It just used that as a broad category. If something doesn't work, it says undefined. Okay. So that limit is not defined. But we know what the graph looks like. So if we approach from the right, we should actually get positive infinity. So let's actually see how you look at something like that. If you go calc, limit, how you enter from the right, 1 divided by x, comma, x, comma, 0. So we're approaching 0. You put an extra comma, and then you just put the number 1. literally the number 1. So that 1 represents x is approaching 0 from the right side. So if you enter here, you realize it now considers the answer infinity. Just puts its little infinity symbol. That's nice. It can tell you about infinite limits and then it's at infinity. By the way, I forgot the, I'm pretty sure that if you want the x to approach infinity, you type out the word infinity or INF. I have to look that up. I looked it up once upon a time. And I forgot. But anyway, if the answer is going to be infinity, it'll tell you. If you wanted to approach from the left, it's a very similar thing. So you go calc, limit 1 divided by x as x approaches 0. From the left, I use this negative symbol here. I'm going to enter a negative 1. So now it gives me the answer of negative infinity. Let's I don't think I wrote down what infinity is. I don't know, I don't think you can type out the entire word. You probably type out a part of the word. 1 divided by x as x approaches.
Isn't the infinity sign?
There's actually an infinity sign on the calculator.
Yeah.
Do you see it? Oh, here.
Yeah.
Yeah, you can actually enter it. It's a direct symbol. Green here. Okay, because I was wondering, I don't think you type out the entire word. Yeah, it's actually, the infinity is a symbol, so you can actually just enter that symbol by pressing the green button and that, or you can press the minus sign, then the green button and that to get negative infinity. So I could go the green button, infinity, close parentheses, and that should give me 0. Yeah, that's our infinity. It's a button. It's actually a button right here. Okay, so we will stop there. Next time, we'll mention a little bit more about limits, and we'll actually talk about the derivatives. So next week is going to be a big deal. Our next test is in 2 weeks. So by next week, I'll post another review, and follow the instructions, go through the review, and follow up in the way I asked you to, and hopefully make the next test a much better one. So that the first text gets dropped and we all forget about it. We'll hear about it until the end of the semester. So I'm dropping one test. For a lot of you, that needs to be the first one. So really, within these next 2 weeks, get serious, start practicing. Practicing in the proper way and testing yourself in the proper way.
So you multiply 2 times 2 is 4 and minus 4 is
We'll stop there.
That's the derivative.
Okay, start over.
So if the original function is 2x squared